That roof is on fire. Oh, we gonna take it high.
Yes, we can do
Don't worry. I think it's fine now. It has recorded. So I was saying, or in applied 1A, you guys dealt with a lot of statics, no motion, and it was just simply F net is equal to 0. So there was no acceleration, there was no velocity, there was no change in position. Hence, you also dealt with moments, like your moments being equal to 0 when we were solving our 3D structures. So which was fine, which was easy, and which was straightforward. So now we are no longer dealing with statics at all. So now you're not gonna do statics. So meaning you're gonna see velocity, acceleration, changing position somewhere, which is not a problem. So now, first thing first that we have to do, man, let me admit someone to the call. Give me a second. How? Now I can't see the person. Okay, they'll come back. So now, in the first thing that we need to do in chapter 3, we need to look in what we call kinematics and path equations. But now it's not a problem because I'm gonna explain each and every weight I put down here. That's very important because I feel like if you just battery low, let me charge my PC. Yes, we're not having. Don't bring a person here. Don't bring your person here. This is a holy house. Let me charge first. So, like I said, we're gonna start with breaking down kinematics and path equations. So we're going to focus on, I'm going to explain each and every way that I put down, right? For you to understand exactly what is it that you're talking about before we even look at the mathematical structure or equations. So 3.1, let me just call it number 1. They are just introducing you to kinematics, ne? Introduction. So this semester, guys, I'm writing a lot of notes down. I think I'm kind of this semester. So first thing first, guys, let's understand the broader field of mechanics. You know what mechanics is. You did physics, like I said, you did 1A, you did introduction to engineering design 1A. Mechanics is the branch of physics, ne? So mechanics, it's a physics that deals with let me admit someone. So mechanics is a branch from physics that deals with motion of objects and their forces. So when you have an object that is in motion, we know that this is subjected to certain forces. That's why the object is moving. You know that from physics. That's mechanics. So the motion of these objects that I'm talking about can be divided into 2 parts. Number 1, we have what you call dynamics. And number 2, you have what you call kinematics, which is the highlight of 3.1. So now let's discuss what dynamics are. So dynamics, first thing first, when you describe these things, you must say it's the study of something, the study of what? This is a study of how a body changes. A body changes. Let me say its state. Its state. So when I say its state, guys, I can say its position, velocity, or acceleration. That's what I mean when I say a body changes its state over time, when it's under certain forces, or let me say when it's under forces. So you know, guys, in Newton's second law, the body is at rest, it's subjected, it has an F net, it starts to accelerate, so it changes its acceleration, it changes its position too. That's what you mean when you say dynamics. So under dynamics, this is governed by Newton's second law, which says F net is equals to your m times acceleration. You know, sometimes, so we used to find the acceleration when you have the F net and when you have the mass of the object. But now, guys, in this module 1, APM 1B, we speak about particles. Okay, what is a particle? In physics, when you refer to a particle, we refer to something very, very tiny. It's so small that we neglect its mass. You understand? That's what you mean when you say particle, but you're going to talk about that. So now I'm interested on my second type of motion that our objects can undergo. We spoke about dynamics, ne? And we spoke it's governed by Newton's second law. We're going to speak about dynamics in chapter 4. But now we're interested in kinematics. So now this is still, okay, let me put it like this. This is still a study of body's motion, ne? This is a study of body's motion. Same as dynamics of body's motion. But this time, remember, guys, on dynamics, I said when it's subjected under certain forces. So here we studied the body's motion without considering the forces that are acting on it. So what are, guys, for now we are not going to talk about considering the forces acting on it, ne? Forces acting on it. So what are, for now we are not going to talk about F net is equals to MA. So yes, our objects are gonna be in motion. They're gonna be in motion, right? But you're not gonna consider the forces that are causing the motion. Remember, when something is in motion, we are curious. What is it that is causing the motion? In most cases, in our mechanics or in our physics, we know it's forces. But now, when you talk about kinematics, we're gonna talk about objects. Let me not say objects. Let me go back to saying particles, because that's what you'll be talking about. Like I said, a particle is just a simplified model. Why? It's making things less complicated, simplified model. Remember, guys, under dynamics, that's when we'll be talking about F net is equals to MA. What are we need the mass of whatever we're working with. So now, under these kinematics, we work with particles. Why? We do not want to have to deal with the mass. So when I say we work with particles, I say these simplified models are very small particles, and these particles, we can neglect the masses. The mass, the shape, the size is negligible. You understand? So, yeah, let's continue. That's the explanation I wanted to give about kinematics and what do you call it, and our dynamics. So now let's speak about something called path equation. So path equation, we are saying, is R at T, ne? So we describe the position of an object with time, type of thing. But let me just dive deeper with explaining the terms so that you get it until we do an example, ne? So imagine a particle, guys, ne? Let me draw a 3D space. This is a 3D space, like a 3D space. You understand? I believe the world we live in is more of a 3D space. You know, usually this is your Z, and this is your X, and this is your Y. You have a particle here, right? When this particle is here, guys, right? When it moves, it makes what you call a trajectory or a trail. So when it moves, it leaves a trail. So we can track the movement of these particles. So this is what you call a trajectory. I don't know how you want to call it, but they don't care. Nobody cares how you call it. Trajectory. Because how I pronounce things, I have like people who know English very well looking at me every time. I'm like, hey man, I do not care as long as I know how to write it, right? So, or if you want to, I want to put it in a way that you understand. Let me say a trail. So this object was it here, position A. I'm gonna call it position A. And the object comes here, and now we call it position B. So this object, like I said, the trail that it followed to move from, these are not two objects, guys. Please pay attention. It's the same object. It's Sana. Sana moved from position A. He came to position B. His path, when we track it, we call it a trajectory, the trail of the path. So now, we are going to have a mathematical way of describing the path that Sana took to move from point A to point B. That's what you're going to call our path equation. Okay, guys, so far, do you understand each other? And if I don't get yes, I'm going to get angry. Guys, do you understand each other?
Yes.
Okay, sharp. So now let me describe few terms that you're gonna put on our space, because sometimes you see them often. Maybe if you're using the textbook or the lecture slides, these are the words you're gonna see. So let me just try to explain some of these words so that even when you're reminding yourself of these things, you don't forget. So make sure it clocks, like it clocks. Number one, we have a word called reference frame. Honestly, first time when I was studying this thing, when I saw reference frame, I'm thinking about window frames. You understand, Mus? One of my brothers thought about someone being framed for murder. I was like, when you need to see psychiatrist. How can you think about such a thing? So when you say reference frame in mechanics, remember, applied mathematics just means we apply your maths in the real world scenarios, like your motion right now as we are doing, your particles moving. So when we describe a position, like when we describe a position of an object, we need a reference frame. For example, guys, if I decide to run, let's say I decide to jog from, I don't know from where, I want to jog. So when I want to jog, I need a starting point, right? I need a starting, or I need somewhere where I'll start. So now when I say I covered 10 kilometers today, I know where I started from. I know where do I measure my distance from somewhere. Same as when it comes to my particle moving from point A to B, I need somewhere where I can measure the position from. So when I say a reference frame, let's say it's just a fixed coordinate system. When I say coordinate system, I say your X, Y, and Z. That you're familiar with because you're familiar with X, Y, Z, all of them. Listen to me, from which you observe the motion. So here, usually in most cases, we take our origin as our reference frame. When I want to measure the position of the object at A, I'm gonna measure it from my reference frame. I'm standing here. So I want to know what's my position. You understand? Now, when it gets to B, it went to another position. So to measure it, I go back to my reference frame. I measure the position from my reference frame. So when we say a particle moving in a fixed reference frame, it means we've set up an origin and axis that don't move. So that axis or whatever the origin is, it does not move, guys. It does not rotate. It's our observation point. That's why we observe the position of the particle at all times. That's what you mean when you say reference frame. We set up our reference frame here. Oh, it means we can observe the motion or our particle moving from this point. Let me call it point B. Or when I say it's 3 kilometers, I mean from point P is 3 kilometers. Now, 3 kilometers is actually big for a particle. How can a tiny particle travel 3 kilometers? But I'm trying to make it as practical as it can be so that you can understand better. With reference frame, guys. So what does it mean? Reference frame. So what are this one is going to be the position of an object, number one. This one is going to be the position of an object, number two. Why do I put T? This is a position with respect to time. Or over time, at any given, uniquely at any given time. Today I'm speaking English. I was sick and I'm getting better. Hey, I'm joking. English makes you worse, but you guys get it. Ne? So guys, with the reference frame, are we clear? So when I say reference frame, I'm not going to hear anybody saying, hey, what? Do we understand each other, guys? Hey, guys, do we understand each other?
Yes, sir.
I said it, guys, or AI must improve. I must be able to slap people through calls. Stop. You understand? Because I can ask you if you guys understand and you keep quiet. Guys, you make me sad because I need to know whatever I'm saying is clicking, is clocking. So, second, let's talk about position vector. We spoke about position vector in a static way last semester in APM 1A, right? So position vector is just the position we were speaking about. Ne? So this is a position. Okay, let me shall I write? Let me just say, let me see, position. So position vector, position of a particle in this reference frame. In this reference frame. When I say in this case, I mean in our APM, our reference frames, ne? Can be represented by what should I say? Yeah, in this reference frame, ne? And so actually, you know, a lot of waiting. I feel like somehow it's let me just draw again. Our particle was here and traveled here, same scenario. So now this is, I said our X, Y, Z is our reference frame, ne? So our particle now, when you check its position relative to the reference frame, now the magnitude of this, or let me not say the magnitude because it sounds like the magnitude, which is a scale. Let me say the vector that is describing this position, which is your RT, that's what you call the position vector. You guys probably remember it from last semester. Ne? This is your position vector to make it easy. To make it easier for you. So remember, guys, the T in here, when I say RT position vector, remember the T means position changes with time. That's what it simply means, changes with time. Okay, I think now let's check the position vectors in 3D space in our APM. In 3D space, how will our position vectors be written like? Number one, our position vector will be written in this way, in this course. It's gonna be x at t. So it's gonna be a certain equation here, which is x with respect to x as a function of t here. You understand? Then they're gonna write this x hat. This x hat, it's a unit vector. It tells us or this is an x direction. You understand? So we're gonna say plus y at t. Or it's gonna be a certain function here as a function of time, and I'm gonna say y hat to show that this is a unit vector which is in the direction of in the y direction. These are unit vector. You x hat, y hat, you did them last semester, guys. So you definitely remember them. Then lastly, we're gonna say z at t, and it's represented by z hat. You understand? Or if you don't want to represent it this way, you can say x at t. All right, guys, remember, if you put brackets, there's no need to put x hat, y hat, z hat. You understand? Y at t and z at t. But how do you see the difference compared to the statics you did last semester? Last semester, it was strictly you needed these brackets to indicate it's a vector. But somehow in these kinematics, they're not that strict. You understand? Because because even in the notes somehow when I was studying last semester when I was doing this course, when I was studying with the notes, they were allowing these brackets. You understand? But the important thing is you can represent it in these two ways. So x at t, you can see there is x at t, here it is. Y at t, you can see it's there. Z at t, it's there, you can see it. A function that tells you the x, y, z coordinates of the particles at any given time. You understand? All right. Okay, let me write it. Hey, I feel like it's not looking. X at t, guys, y at t, z at t are functions that tells you x, y, z coordinates of the particles at any given time, t. Guys, don't mind the pause. There is a guy frying eggs with water behind me. So then another thing, don't forget this. X hat, y hat, z hat are unit vectors that tells you the directions along your x, y, and z axis respectively, right? So far, so good, guys. I know, a bit by bit. So tell me, so far, so good. Guys, so far, so good. Position vector, how we represent them now, because we'll be working with 3D space and how we represent them in 3D. For our path equations. Guys, so far, so good now. So far, so good.
Yes.
So, Vumanivo.
So,
But you might asking why is this guy telling us about position vector? If you know position vector, so actually we call it position vector function, ne? Position vector function. To sound professional, or in class, if in case you're asking a question or giving an answer, don't just say position vector. You are embarrassing me. You must represent me well. Position vector function to hear your story. So why, guys, position vector function? If you know about position vector, we are saying you know everything about kinematics of the particle. Ne? You know what a kinematic is. You know what a particle is. So now we're describing that kinematics of that particle. So when you know your position vector function, you know everything about kinematic. Why? Because from this, you can find the position of an object at any time. So therefore, you can derive from the position, you can derive your velocity of the particle, then you can derive, let me just say, an acceleration. Hey, who taught me English? So overall, guys, from the position vector function, you got the position. From that, you can derive velocity and acceleration. For example, let's say, imagine a particle, excuse, yeah, imagine a particle maybe at time t0. So t naught, let me say t naught, at time t naught. So this particle, guys, it moves to another time tf. All right, it was at time to, it moves to tf. So it means, guys, its position here is r at t naught, right? So what its position is gonna change to what? This position is gonna change to r at time f. You understand now? So what are now between, okay, when the object move from t naught to tf, there is a path. We can trace the path, right? What do we call the path, guys? When I listen, guys, what do you call the path when we trace it? When it moves from time t naught and it moves from time it moves to time tf. What do you call the path, guys? As we trace it, as we trace the particle.
The trail.
Trail, yes, but what was the word, Kunji? The official word? Because I only use trail so that you guys get it. But I said, what's the official word?
The trajectory.
Trajectory. Okay. Okay, guys. Let's take an example. Let's look at an example. So, let's say they give us a position vector function. RT is equals to tx plus t squared minus 1 y hat. So now let's interpret this. Is this a 2D? Is this a 2D or a 3D problem? This particle, is it in a 2D space or a 3D space? First thing first, that's what you need to identify.
2D.
It's a what?
2D.
Okay. Can somebody different tell me why is it in a 2D space?
Say we only have x and y, there is no z component.
If you go back here to our equation, you can see, oh, this guy z at t is 0. So you can see, oh, our z at t is 0. So this is a 2D problem. So now we have to identify individual coordinate functions. What do I mean when I say individual coordinate function? I mean this guy is a first coordinate function and this guy is a second coordinate function. So help me identify my x at t and help me identify my y at t. Let's go. What's my x at t, guys?
It's t.
Is t, right? So this is t. Then what's my y at t?
T squared minus 1.
T squared minus 1. So now they're challenging you. So now we need to visualize the path. Well, guys, I need to see how will my object travel. I need to see. Good. I need to visual. Good. I need to know what will my object path look this way. Or will it look this way? Or will it look this way? Or will it look this way? Oh no, that's actually my name. There's no way an object can travel, Sana, but you get it. So, so how are we going to do? Because we need to visualize the path. Visualize, because they might ask you to sketch the path of an object. So that's why it's important to visualize the path. Okay, what can we do? What's the method? We need to find the relationship between x and y. That doesn't depend on time t. All right, we need a relationship between this guy and this guy without t being involved. Okay, what can we do? Are you aware or we can substitute our x at t into the equation here, y at t? You realize or actually, it just means x is equals to t according to the first equation. Do you see that?
Yes.
Guys, so when we take this guy, we substituting him here. We said x is equals to t. What are on the second equation? Where there is a t, we can put our x. So you can see what y at t It can change. It's no longer a function of t. We change it to a function of x. So y at x, because now we're eliminating the t, we're putting an x. So it becomes the function of x. This becomes x squared minus 1. Can you visualize the path? Can you visualize the path? Can you plot the path? Can you see what kind of a path is this? Yo, guys, the English is making my tongue go loco, but you get it. Can you visualize the path now? Can you see the type of a path the object is going to travel? Who can tell me, according to our new equation, which depicts the relationship between our x and y without involving t? How, guys? Guysini?
Oh, it's a parabola that has moved 1 unit downwards.
Yeah, 1 unit downward, 10B, but yeah, I get what you're saying. So we can see, oh, this is actually a parabolic. But how do you sketch? Do I just do this and say, pew, there we go? Oh, you said 1 unit downwards. No, I never did functions. Oh, like this. Do I just write this? How do I do this? That's the question. Okay, so we know originally both x and y are functions of t, because what does it mean, guys? Our object, when it travels that parabolic path, now that's a trajectory, but that's our trajectory. It changes with time, because remember, our x was function of time, y was function. So meaning, actually, whereas our object travels, it travels, time changes. Or here is different time, different time, different time, different time, different time, different. You understand? So what are on your sketch all the time, because you must indicate that. Failure to indicate that, you are dead in the test. So now I'm gonna make a little table. So I'm gonna say this is t. So my t, I'm gonna start it at 0. You can't start yeah, I'm gonna start my t at 0. Ne? So I'm gonna say 0, 1 only. I'm just gonna say 0 and 1. I no need to write a lot of things. So when t is 0, I go back to this equation here. Y at t equals to t squared. Where there is t, I put 0. So actually, let me just say x, y. Actually, let me start with x. When I put t 0, what's my x? 0. When I put on my y equation as a function of time, when I put t 0, this becomes -1. Ne? So now I'm coming to where t is 1. You can go to t up to, I don't know, you can go as long as you want with the t's, guys. But somehow you're gonna jam. So just keep it short and simple. So sometimes they can give you like a range of t's. They can say from 0 to 3. You understand? They want to see the path of a particle between 0 and 3. Or you're gonna start from 0 to 3. So where t is 1, x is just 1. Here 1, it becomes 0. Okay, now let's check. The first one, at r, it's equals to, why am I saying r equals to 0? At r, when I put t 0, what's my vector, what's my function, my vector function actually for the path? It becomes 0. My position vector function, ne? When my t is equals to 0, it's 0 and -1 according to this. Can you see that? Then where my t is 1, my position vector function becomes what? My x becomes 1 and 0. Can you see that, guys? Oh, guys, can you see that before I sketch?
Yes,
Okay,
yes.
perfect. So now I'm going to sketch my thing. So when I sketch my thing, I know how you said it's a parabola at -1. You are right. So let's check. I have 0, -1. 0, -1, where is it? Where x is 0, y is -1. X 0, y -1. Is it this side? No, x is not 0 here. It's here. It's right here at the turning point, isn't it? Here, x is 0 here, and y is -1. Then another coordinate where x is 1, y is 0. It's somewhere here. 1, 0. You understand? So my path so far, it's only gonna be this part. You understand? It's only gonna be that part. Unless maybe if let's assume here there is maybe they restricted my t to be from 0 to 1 only. But if they didn't restrict, I can just go on and go and even decide and go on. But for me, for now, for simple simplicity purposes, I'm just gonna keep it from t equals to 0 to t equals to 1. So now you are not done, guys. You need to indicate, or here is where t is equals to 0. Then here you must indicate that t is equals to 1. You are also not done. You need to indicate the direction of your particle. So you must put an arrow. It moves from here to there. You must put like this. Then now you're gonna get full marks. That's when now they say that's when they will ask you to plot the path of your particle. You must sketch it. So you must indicate all this. You must indicate your t's, your times at different points. So sometimes you'll sketch like a path looking like this. Or you must start from the middle and name and show, or is it coiling clockwise or anti-clockwise? But no problem, because we're gonna do even past papers a lot. So you're gonna see all those things there. But for now, this is for you to understand for now. Are we fine, guys? Can you take another example? With this example, do you know now what's needed when you have to sketch and show the path of your object, your trajectory, when you are given your position vector equation? Are we fine with that one? Hi, guys, we don't have time. Claire, please confirm.
Yes, sir.
Oh, okay. I want to give you another problem. Ne? Actually, today, you're not solving anything for me as a classwork or anything, because we're just starting. Ne? Let me take another example. I feel like with the examples, I see how they work with engineering maths. Examples help you, especially if like that type of an example that you can find in the test or an exam. Okay, now this time they gave us the problem. I have acceleration vector equation. Like I said, kinematics starts from position vector equation. Then from that, you can move to acceleration vector equation by deriving and all of that. You know the story. So now, let's say you're given these. Ne? You're given A at t. It's equals to 2t and E at t. Okay, before that, okay, you know what? It's fine. Let's continue with the problem. Let me not complicate things for you. So now, on this problem, we are given what you call initial conditions. Actually, these are problems that people get wrong in the test for some reason. So you're given these initial conditions, guys. They are telling you the position at where t is equals to 2, or at 2 seconds, but where t is equals to 2. They tell you or no, the position vector equation there, or function, it's 0, -1, 2, right? And they're telling you where v at the same point, or v at where t is equals to 2, they're telling you it's actually 5, 0, 0. So listen what the question says. They're asking you to find, they want you to find r at 0 and v at 1. Yeah, no, no. Okay, let's recheck the question. They gave you acceleration vector equation, guys. A at t is equal to 2t E at t. So they gave you certain initial condition. They're like r at 2. Now this is where t is equal to 2. You understand? And even here is still t equals to 2. But the first one is still position, but not the position of this particle where t is equal to 2. They gave it to you. But this is your x at t, this is your y at t, this is your z at t. Don't forget. But they gave you the velocity at the same point where t is equal to 2, s500. So now I want to ask you from these initial conditions and the equation they gave you for acceleration, they want you to find the position of the particle where t is equal to 0. You can see it's r at 0, and the velocity where t is equal to 1. You can see it's v at 1. So far, before I start with solving the problem, are we together, guys? Is everybody still awake? Guys, is everybody still awake? Give me a second. Yes. She's what? Leave her. I think it's because I must have for 3 days. You must have for 3 days. No, it makes sense, my guy. Hey. Okay, guys, let's continue. Are we together? Guys, are we together? Oh, 8 people in the call, and I don't even get a single yes. Guys, are we together? Before I start, are we together?
Stop.
I just want to know so far is everything clear. I haven't started solving the problem. So I want to know so far, are we clear? This is probably going to be the last problem for the session. Ne? Yeah. For today's session. So are we together, guys, so far? I need to know if you are still awake or you are sleeping now. Maravanna. Guys, are we together?
Say this question.
Yes.
So you can continue the question.
Okay. I thought you had a question. But now, let's check, guys. We have acceleration vector equation. Let's forget about the initial conditions for now. Let's check if they give us an acceleration vector equation. So here we can see there is velocity involved and there is position involved. Somewhere, somehow, guys, we need to find equations for velocity and position. Or from acceleration to velocity, how do we go there? Damn it. We definitely need to integrate. Do you remember that, guys? To move from acceleration to velocity, you need to integrate. Or to move, then we can integrate again to move from velocity to position. Are we together? Remember, guys, acceleration is the rate of change of velocity. So to go from acceleration to velocity, we need to integrate. So let's take the equation for acceleration. Okay, let's check. It's let me write it where I can see it on the new page. Ne? So it was a t. Anybody who wrote it down? What was it? It was 2 and what?
T.
T.
And e to the power t.
E to the power t. Right. Okay, now let's start. We know v at t. To get v at t, we need to integrate a at t with respect to t. Hence, I'm saying dt there. So now let's start. I'm gonna say my v at t is gonna be integral of what is that? 2t e at t dt. Oh, what does it mean? We're gonna integrate each component separately, right? Or we're gonna integrate the x component separately, the y component separately, and the z component. So now I'm gonna start integrating the x component. What's the integral of 2? What's the integral of 2, guys?
2t.
2t. What's missing? This is an indefinite integral. It doesn't have boundaries. So what do I need?
Plus c.
Plus c. But I have to say c1. Why am I saying cy? I have 3 components there because every component must have its own constant, right? Now I'm integrating the second thing, which is my t. So I'm going to say t dt. It's equals to, what's the integral of t, guys? That's a power rule. It's going to be 1 plus 1 squared, 1 over 2. So it's 1 over 2 t squared plus. Now, this is a second component, right? So I must say plus C2. That's a second constant for my second component, which is my Y component I just integrated. So now I'm coming to the third component, which is my E to the exponent T. Guys, what's the integral of E to the exponent T?
E to the power t plus c.
So it's e to the power t plus c3. Okay, let's write it properly now. Let's stretch it out and write our own velocity equation. So it's gonna be v at t, right? It's equals to. So now I want to write it in this way, in the brackets form, because with the x hat, y hat, I feel like it's gonna mess with my head. But you can write it that way, no problem. I want to write it so I can see it neatly. So the first one was it the 2? Yeah, so it was 2t plus c1, Then the second one is half t squared plus c2, right? Then the third one is, there it is, e to the exponent t plus c3. That's my velocity. But let's check. We know c1, c2, and C3 are integration constants. We need to find the values. How do we find the values? We're given initial conditions. You use those initial conditions. Okay, now let's start. So what does it mean? We know our our initial conditions that, again now guys, this is the equation for velocity function, but it has C1, C2, those integration constants. We don't want those. They're not going to help us. So we are going to take initial condition that involves velocity and use it. Let's see, which one is it? Is the one that says V at 2 is equals to 500. I'm going to use that one. Ne? That's the initial condition I'm going to use. So I'm going to say V at 2, remember it's 5 at 0, right? Ne? Remember, this means, I told you this means this is where T is equals to 2. I need you guys. So what are we going to do? We're just simply going to substitute T is equals to 2 on our equation here. Can we do that? Let's do that. So V at 2, using our vector equation for velocity there. Why am I still writing T there? Hey, what's it? So V at 2 here is going to be equals to. So when I substitute 2 here, what do I get? 4 plus C1. When I substitute 2 here, I get 4 over 2, ne? Which is 2. So it's 2 plus C2 plus plus I managed the fluid getting to my head. So this is E. What? Yeah, it's just E to the exponent 2 plus C3. We are fine, Aniti, guys. Guys, are we fine so far? Okay.
Yes.
No. Okay. We know this is the same particle, same path, velocity the same. More like T equals to 2 is just the same path on the same. Good guys, it's just the same velocity. Do you agree with these two guys are equal? Do you agree with these 500 and these are equal? Do you agree? So do you agree? Will you agree with me if I say 4 plus C1 it's equals to 5? And will you agree with me when I say 2 plus C2 it's equals to 0? Will you agree with me when I say E to the exponent T plus C3 it's equals to 0? Do you agree with me? No, man, it's 2 here. Does everybody agree with me? Do you agree with me? So we can solve them. How much is C1, guys? Fast solvers.
1.
It's 1. How much is C2?
Negative 2.
Negative 2. What's my C3? Negative E squared. Because I feel like E squared if you punch it on the calculator. So now we're going to substitute. We're going to substitute the constants. Now we get our vector equation. Ne? So when I say C1, so it's gonna be when I substitute. Hey, holy smoke! Panna, where is this line coming from, Manj? So my VAT is gonna be here. What's the equation? Oh, 2T. Then what's my constant? It's my C1. Remember, my 2T was with my C1. I found C1 as 1. So it's gonna be C1 plus 1 here. Then I'm gonna have 2 plus C2. No, man. I need to substitute on the original vector equation for velocity that I found. Ne? So it's 1 over 2T squared minus 2. 1 over 2T squared minus 2. Then I come to the third component there, which is here. E to the exponent T plus, what am I C is gonna be minus E squared because it was C3. So it's E T minus E squared. So remember, what's my equation? What was the equation, guys? Find V naught, find R at naught and V at 1, right? So now I found my velocity equation. What are guys? I can find my V at 1, right? By simple substitution. Now, no sweat, like easy like that. So now you substitute where there is T, you put 1 because they say find V at 1 or where T equals to 1. That's what it means. So on the first one, guys, when I put 1 where there is T, what do I find? Guys, all of you are math students, guys. You got into engineering because you passed maths very well. So 2 times 1 plus 1, how much?
3.
3. Let's go. Half t half over 1 over 2 into 1 squared minus 2. How much is it?
Negative 3 over 2.
That one angeke ulunge mfana. So it's e minus e squared. That's it. So we found our v1. Order for this question, we got 50%. But there's still a problem, guys. Are you aware or we haven't found the equation for our position? Remember, they want r at naught. That's what the other question was saying. They want r at naught. What are the position at? But remember, we only had the equation, the vector equation for our acceleration. We're able to integrate to go to velocity. So how do we get to position, guys?
You have to integrate again.
Yeah. So yes, to get to position, we need to integrate again. But this time, we integrate the equation of the velocity that you got. So, all right, guys, if you can't get velocity equation, you can't get position, or you carry 0 from the semester test for this question. Guys, chapter 4 is so weird. You understand? But I promise you, I'm going to make it as easy as you can get. And I'm going to prepare you for the worst. You understand? Because the average for semester 2, test 2 last year was like 11 or 10%. I forgot, but it was very low. So I'm going to prepare you for everything that you can get. You understand? So all I need for you guys, please attend. I can't emphasize. Guys, for this, Kambe guys was keeper my 10B classes. If you're part of my 10B class, that one at least, guys, you can recover from recording. So this one, I need you to come to live classes, not just recordings. Recordings alone are not enough. Okay, so my RT, I'm gonna integrate. What's my VAT equation? I'm sure someone wrote it down somewhere. Just call it for me. Oh, guys, someone I'm sure wrote it down. Just call it for me to save time, Claire.
It's 2t plus 1.
Mm-hmm.
Then half t squared minus 2.
Mm-hmm.
Then e to the power of 2 minus e squared.
It was e to the power t minus e squared. Yeah, I remember that one. So dt, same thing we did, guys. We're gonna integrate each component separately. So what are we gonna start with integrating 2t plus 1 dt? This gives me let me check. When I add 1 plus 1 is 2, 2 over 2, 2 cancels 2. So here I'm just left with t squared plus t. I already used c, ne? So these constants, I'm gonna call this one d1. d1, and the second component was half t squared minus 2 dt. It's equals to, what's the integration of these guys? 2 plus 1 is 3. 1 over 3 times 1 over 2 is 1 over 6. So I have 1 over 6, 1 over 6 t cubed, ne? Minus, this is just 2t. Or this one, I'm gonna call it 2 d2, I mean this constant, because it's for the second component. I'm sure now you already know the drill, right? So the third component there, it's e to the t minus e squared. So dt, this one is nice. It's just e to the t minus e squared. It's a constant, so it's just e squared t, right? When you integrate, plus d3. So now let me write my position vector equation, ne? With the constants, of course, like I did with the velocity. So this one is going to be t squared plus t plus d1, right? 1 over 6 t cubed minus 2t plus d2, right? Then the last component here is et minus e squared t plus d3, right? Perfect. Now I write it. So now we go back to initial conditions. We need initial conditions for positions. They're gonna help us figure out the constants, remember? So now I'm going to go up there. So Zulume some papa easy. Oh, they gave me R2 S0 negative 1 2. R2. Hey guys, I'm forgetful. So I know my R2 was what's my R2, guys? Gonje?
0, negative 1, and 2.
And 2. Perfect. So what do we do, Gonje? Who can tell me what's the next step? Little man with some papa easy. Guys, what's the next step, Gonje?
You substitute the 2 in with the t there.
I substitute between.
You replace the t's with 2.
Yes, on this equation that has constants, where there is t, I'm gonna put 2. Ne? So it's gonna be r at t. Good, I'm being controlled by my initial condition. So if they said r at 3, here I was gonna, where there is t, I was gonna substitute 3. Hold on, now I need r at 2 from my vector equation for position. Ne? So when I put 2 here, I get 2 squared is what? 4. 4 plus 2 becomes 6, right? To save time. So this is going to become, this becomes 6. 6 plus d1. Can someone substitute? I don't have a calculator next to me. 1 over 6 into 2 cubed minus 2 into 2. Can someone tell me what is it? Guys, send some medication my way. Yo. I haven't seen Compass in a while. I even forgot where the gates. Ish. Guys, please, I'm running out of time. Okay.
It's negative 10 over 3.
Negative what?
Negative 10 over 3.
Okay. So it's negative 10 over 3 plus d2. Then the last one. The last one I think is pretty easy. When you put 2 here and 2 here, it becomes negative e squared because it's now 1 e squared subtracting 2 e squared. I'm trying to polarize them. So this is d3. What's the next step? Who can tell me the next step, guys?
We equate.
We equate with the initial conditions. So 6 plus d1 is 0 minus 10 over 3 plus d2 is equals to negative 1 minus e squared plus d3 is equals to 2. So now let's solve. Ne? So I see what d1 is equals to negative 6. D2, can someone press the calculator? 10 over 3 minus 1, how much is it? This is 10 over 3 minus 3 over 3. So this is 7 over 3. And E3, this is just going to be 2 plus E squared. So now I'm going to rewrite my position, a position vector equation. So my R at T, now I just substitute without constants. It's going to be E squared plus T plus, guys, don't take, remember, guys, don't forget we are trying to find constants and you must come back to this equation. That's what you want. So E squared plus T. So this is going to be E squared plus T plus 6. We have it now. So we come back here. 1 over 6 T squared minus 2T. 1 over 6, no, it's T cubed minus. Guys, I'm sorry. When I'm writing, I make a mess. Hey, what's the way? What's my D2 plus 7 over 3? Then what's the last one?
What's that?
ET minus E squared T. ET minus E squared T plus 2 plus ET. Yeah, that's it. So remember, the question wanted R at naught. So now you have your full position vector equation. So now you can find R at naught. Or where there is T, you can put 0, guys. So when I put 0 here, I'm just having, what is this? This was E to the exponent T. So this becomes 1. 1 plus 6 becomes 7. So here I put 0, this goes, 0, this goes. This is just 7 over 3. 0, this goes, 0, this goes, 0, this becomes 1, then 0, this goes, 1 plus 2 is 3, so this becomes 3 plus E squared. So this is your second answer, 100% done. Guys, with 3.1 and 3.2 now, are you, I know we're still gonna do some problems here and there, especially from your past papers. Most of these questions I read them from your tutorials and your papers. But my aim is to explain as much as I can before I rush into questions so you get the concepts from kinematics and to all the other branches that involved, including a path equation, which is one of the important things. So, guys, that's it from me for today. So, I just had to host the session so you guys don't fall behind. I'm gonna host another one this week, probably because you guys are behind. So I'm gonna host remember we host me and Muluko host Matena. Why am I saying Maten? Maten be Wednesdays and these days. So maybe I can squeeze this one Friday or somewhere somehow, but I'll definitely. Okay, guys, how was the session?
Physics, you
know, as Pelele, I want to mute you, but it says I must remove you. How was the session, guys?
It was good, sir, but it was short.
Eh?
It was short.
It was short, ne?
Mm.
Yeah, being sick. Now I'm already sweating. I feel like I've been talking for Boma 2 hours. Can't know. It's only been an hour. It's okay. I'll get back on form. Don't worry. And others, how's the session, guys?
It's good.
Yeah, Patrice. Thank you for always attending. Today you attended in a taxi. That's a good thing. That's dedication. Wang Tol. And they're educative but short. Oh, okay. Next time I must push for 2 hours. For me to push 2 hours, guys, you must send medication my way. Or else, I'll be sick the whole week. Well, I've been sick from Wednesday last week till today. So you must send meds my way so that I'm better and I'm able to host a longer session. Imagine if you can cover the semester test 1 content in like 3 sessions. That's what I aim for. You understand? So in the next 2 or 3 sessions, you must cover everything so that we quickly move to chapter 4. Actually, no. In the next 2 sessions, we'll definitely cover the whole of semester test 1 content. So semester test 1, we'll have covered your dot notation. We'll have covered everything actually that you need. Also, how to do the proofs using the dot notation. So next session, guys, and the next one. So the next 2 sessions, unless if Mpho decides or they bring that tutor who's busy procrastinating. But as for me, guys, the next 2 sessions will cover the first semester test content. Ne? And yes, Patrice, do you have something to say?
Saying we don't want that tutor there. You must teach us.
Yeah?
We don't want him. You can teach us.
I'll tell him, Paul. Patrice, they don't want him, Kalala. Okay, noted. I'll talk to him so I can permanently tutor APM 1B if he agrees. Because at the beginning of the semester, the plan was I'm going to tutor Maten B and APM. I was like, nah, man, you have a lot on your plate. I'm like, this guy, how do you know that what's on my plate? But it's okay. But he's just a brother, guys. He's just being a brother. But we must finish semester test on content in the next 2 sessions. And in the first semester test, I want to see 90s, Nothing makes me smile like a 90 from someone I'm tutoring. It makes me happy, guys. Like it makes my day. You understand? It makes my day. Nothing makes me happy. Not food. Nothing makes me happy like that. Not even my own marks makes me that happy. Because changing someone's life is actually a bigger deal than changing yours. I'm not saying prioritize other people's lives. No. You understand? But anyway, guys, thank you for attending. And go attempt some tutorial 1 questions. Attempt them. You understand? You and I are gonna, this module has 12 tutorials. You understand? So you don't have to attend your tutorials at campus, but attend them, you understand, for extra help. But I'm gonna make sure if there is a question there that makes you understand, I'm gonna make sure I help you with the question and you understand. Anyway, guys, I want to see distinctions in your first semester test. Then we're gonna focus on chapter 4 for your second semester test. Anyway, guys, good night. Let me go back to bed like a sick person I am. Bye-bye. Oh, listen to Nasty C. Zulu Mel, some pow, 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 pow.